Welcome to the video on arcs and chords. A central angle of a circle is an angle whose vertex is in the center of the circle. So this central angle is right here. If the central angle is less than 180 degrees, then the points on the circle that lie on the interior of that central angle form a minor arc. So they're talking about these points right here. Points not in the minor arc are considered points in the major arc, so everywhere else in that blue area. A semicircle is formed if the central angle is exactly 180 degrees. And now this next point is a little different from book to book, but in our book, minor arcs are named with 2 capital letters. Major arcs would be named with 3 capital letters. So they wouldn't call this arc AB and then mean go all the way around. You would have to use 3 letters. So this would be, let's change colors. This purple arc would be BDA or ADB, but you would have to use 3 letters for any arc that is 180 degrees or bigger. The measure of an entire circle, the arcs in an entire circle is 360 degrees. So the measure of a minor arc is the measure of the same as its central angle. So here we're told that this angle is 50 degrees. So this arc here is 50 degrees. We use this expression here just to represent the measure of arc AB. Just like we would use the M and the angle symbol to express the measure of an angle. This is the notation for measure of an arc. The measure of a major arc is simply 360 degrees minus the measure of its related minor arc. So we would see that if we wanted to find this major arc, which I'm coloring right now in purple, we would have to take 360 minus 50. The measure, the measure of a semicircle, once again, is 180 degrees. The arc addition postulate says that the measure of an arc formed by 2 adjacent arcs is the sum of the measure of the 2 arcs. So here's just what we mean by that. So arc AB is adjacent to arc BC. It means it's next to it and there's no other points in between them. So the measure of this large arc, which will be in baby blue, here, ABC, would be simply adding up AB and BC. Anytime that you have a circle or 2 congruent circles, congruent arcs are arcs that have the same measure, but notice it has to be congruent circles or within the same circle. A few more theorems. In a circle or congruent circles, first theorem says that congruent central angles have congruent chords. So what exactly does that mean? Well, here's a picture of a circle. We have 2 central angles. I know that they are central because they both have a vertex there at the center of the circle here. If those 2 angles are equal, then the chords that we would draw opposite those angles are also equal. So it's like saying, if this happens, then these segments are congruent. Also true when in a circle or in congruent circles, congruent chords have congruent arcs. So what that means is that if we have a situation where we have congruent chords, so this line is equal to this line, we can conclude that these arcs are also equal to each other. And last but not least, in a circle or in congruent circles, congruent arcs have congruent central angles. So this is sort of like the converse of number 1. It says that here we have a circle. We have an arc here. We have an arc here. If those arcs are congruent, then these two angles here are also congruent. The next theorem says that in a circle, if the radius or diameter is perpendicular to a chord, then it also bisects the chord and its arc. So what that means is if we have a circle with a radius drawn in, it could be a diameter. Here's a radius. I know it's a radius because it goes through the center and touches the edge of the circle. And it's perpendicular to any chord. So we just happen to have this blue chord here. It could be any chord anywhere on that circle. If it's perpendicular, then what happens is those two segments have been bisected, and also this arc is equal to this arc. In a circle, the perpendicular bisector of a chord is the radius or the diameter. So what that means is that if you have a situation like this where we know that this blue line here is cut in half. I know it's cut in half because these are equal, and I know it's a bisect or a perpendicular because of that box, so that makes that black segment a perpendicular bisector of the blue segment. That means that that original black segment is the radius or the diameter of that circle. Okay, rather than start going over examples in this lesson video, I'm using a software that only allows me 15 minutes at a time. We are going to continue the rest of this lesson on to video number 2.